Speaker now is Dr. Alexander McDonald, is the Chief Science Advisor of NOAA Research and Director of the NOAA Earth System Research Laboratory here in Boulder, President of the American Meteorological Society, inventor of Science on a Sphere, and winner of the Presidential Rank Awards. It's a great pleasure to have you here.
Okay, well, we're on the home stretch. It's a long morning, tremendous talks, but we're going to do a little experiment right now, and that is we're going to do the mid presentation aerobics. So I want everybody to stand up. Everybody stand up on your feet, away from your PCs and your Macs. And all I want to do is for 10 seconds, I want you to move your feet a little bit. All right, it's easy, 10 seconds. Okay, a little energy. Okay, back in your seats. All right. So all I really wanted was to get a little blood back into your heads. It's a long time. I'm going to try and make up a little time. But I think the presentation you're going to get is important. And I really think it's a little bit complex, so I found people take some time. So the title of the presentation is, Can the World's Carbon Dioxide Be Stopped Short of a Doubling? I have my name and Christopher Clack, who's giving a couple of other talks, so you can find more detail on this study that we've done from Christopher and his talks later today. I think one's at 12:10 and one's, I think, maybe something like 2:40. So I want to say that I'm a very fortunate person. For 10 years, I've run a NOAA lab, the largest NOAA laboratory. It's got a significant annual budget, 600 really talented people. And so a lot of what I'm presenting, I'm talking about our laboratory. For example, we have a lot of expertise in weather and climate. And if there's anything that affects energy, it is weather and climate. Climate is our problem, greenhouse gases. And weather actually is an answer, something I'm going to try and get further into in this short talk. So my main points are: one, time has run out on little solutions to carbon emissions. Now, what do I mean by little? Sort of like David McKay's little. He says if everybody does a little, we'll accomplish a little. But the carbon dioxide and greenhouse gas problem is not big, it's giant. It's extremely difficult. It's extremely difficult in a world with growing population where the people of this earth have a right to live good lives with the kind of advanced capabilities that all of us aspire to in terms of our lives. So we need big solutions. I want to say that Amory Lovins has big solutions, and much of what he talked about I think are a part of it, but I don't think it's enough. You can't just solve this sort of on the local scale. It is going to take governments and large-scale solutions. So I'm going to talk briefly in the middle of this talk about a solution to decarbonize the electric sector that our laboratory has worked on for 6 years. And I'm saying we don't have to 2050. We actually have to make huge progress by 2030. And a further really important point, that you can't get out of this problem by doubling or tripling your cost of energy. It has to be done with energy costs that are not much different than today. Otherwise, it just won't happen politically. And finally, decarbonizing electricity is a necessary condition to decarbonize the other sectors like transportation, home heating, and so on. And I think you saw that very nicely in Dr. Lovin's presentation, but I'm going to come back to it briefly. So those 3 points: we're in a very urgent situation. We have to do something now. That something has to be without increasing the cost of energy. And if we do that now, then we have the opportunity to convert the other sectors. Here's something I call the Hoffman curve. As director of NOAA's Earth System Research Laboratory, I was privileged to have David Hoffman running our global network, including the Mauna Loa famous carbon dioxide record, and that goes back to the 50s. David came into me one day and he said, you know, really people aren't looking at carbon dioxide growth right. He said that the real way to look at it is on a logarithmic diagram. And I said, you need to publish this, David, because it really does reveal what's happening. So on the left axis here, you see a logarithm of the where we've subtracted off the pre-industrial carbon dioxide. So this is just the growth of carbon dioxide beyond what it was pre-industrially on a logarithmic scale. And on the bottom, we have the time from 1950 on. So what you see is it's a nice straight line on a logarithmic diagram, and sadly, all these things that you've heard about, everybody's doing their little bit. Sadly, nothing has really changed our slope. So I presented this at COP15 at Copenhagen and pointed out we're still on an exponential growth rate. In David's paper, which is referenced here, he points out that you have the growth of population, and where population growth slows down very nicely, economic per capita carbon emissions increase, like happens in China. So what we have is a world conundrum. We want people to live good lives, but the route right now is mostly through fossil fuels, as has been pointed out already in this meeting. So if we follow this line, the David Hoffman curve, which is really a straight line, we end up in 2054, that hasn't changed, with a doubling of carbon dioxide. So that's where we're heading. Now, I talked to one of our negotiators at Copenhagen. They were all there and everybody was celebrating, and so it was over a beer. So I said, you know, we really aren't doing anything significant. Doesn't look like we're going to do anything significant, and yet this is a giant problem. He said, well, there's a little bit of an emperor, you know, has no clothes thing here. No nation, whether it's autocratic, whether it's democratic, no nation, politician is ever going to really cut down on their energy use unless, and use low carbon energy unless they can do it without big increases in energy costs. And I said, well, I'm pretty sure, you know, I've read these studies, you know, renewable energy, it all works. So he said, go read them more carefully. There are no studies that show that combination of a big increase, a big decrease in carbon dioxide and the same energy costs. So I went back, did a lot of research, worked with people in ESRL, Earth System Research Lab. He was absolutely right. There is, at least in 2010, 2009 when this happened, there was nothing. But the really interesting thing I found was that the weather studies treated weather wrong. There's an aspect of weather that people had vastly misunderstood, and I think that key to that is weather is large scale. If you want to take advantage of weather and renewable energy for wind and solar energy, you have to have a systems large scale. So I'm going to talk about that. This is another diagram that came from our lab, Peter Tan's. He basically looks at if you turn around the total fossil fuel emissions by 2050, right here. Can't do this. I'm going to just use my pointer here. If you turn them around by 2050, you end up with an overshoot to over 700 parts per million of carbon dioxide, and you're stuck with that for years. So I just want to make an interpretation. We're a climate lab as well as a weather lab. I want to interpret that for you. So we're now making a decision. Right now, 2015, we're making a decision. The decision is, what are we going to do right now? So we're making a commitment. If we don't do something right now in the next 15 years, one thing that I think you're going to see is a large negative impact on food production, both agriculture due to changes in temperature and moisture, and fisheries. And we're looking toward a world of 10 billion people late in this century. Here in the IPCC AR5, the last one, it shows that, for example, eastern Colorado, I have a little picture of eastern Colorado here, which right now is very productive. It grows a lot of wheat. But if you take the temperature and the summer precipitation for 2100, this is what it should look like. That's what West Texas and northern Mexico look like. So it's not an area to grow food. So one thing we have to think about as we make this decision of what we do is what's going to happen to food production. A second thing is sea level rise. John Englander has done a very nice book, and he discusses a lot of aspects of this. If you take, for example, the rise of 5 degrees Celsius since the last ice age, it comes out to about 20 meters per degree Celsius. Now, some people say, well, wait a minute, 100 feet of sea level rise, I thought it was 3 feet. Well, that's true, 3 feet by 2100, but you're committed. So you're ultimately going to have that 100 feet because of what we do now. So that's a commitment to 100 feet. It might take 500 years, but we're committed our future generations to that. And then finally, vast changes to the natural biological world. I don't think anybody could do a better job than Elizabeth Colbert, although Leakey some years back had a book by a very similar name and said the same thing. We are really going to hurt the biological world. So we've got a fork in the road we have to decide. One of the key issues here is an economic issue. Nicholas Stern has been a leader in this area. He's got a new book called Why Are We Waiting? The Logic, Urgency, and Promise of Tackling Climate Change. An interesting critique of Dr. Stern's book basically said he did not put enough emphasis. It's amazing as an economist. This was in Nature magazine. It's amazing. He didn't put enough emphasis on recognizing that this political truth, that you can't have a shift, a large-scale global shift to non-carbon energy if you can't do it at similar energy prices. So I'm now going to talk about a paper that we recently submitted to Science magazine called Cost Competitive Reduction of Carbon Emissions of Up to 80% from the U.S. Electric Sector by 2030. I loved Amory Lovin's picture of New York in 1900 with all horses and buggies. 1913, all autos. So we're talking about the same thing. Can we convert rapidly in an economy like the United States? And if so, how are you going to do it and keep the energy prices low? Well, here's kind of what we worked on in the study. This study took 6 years. Really fabulous people that I've worked with. I really hope that you'll go to Chris Clack's talk this afternoon. Essentially, if you look at North America, what you see is that there are areas where wind power can be had pretty cheaply. I call this whole red area that goes from northern Maine across the plains, I call this the wind triangle, because in these red areas, you can buy wind at the turbine for 3 or 4 cents. So that says something right away. Wait a minute, there's really cheap wind power available, but our problem is there's other areas where it's not cheap at all. Look at Southeast United States, look at most of the West, look at the valleys and the coast where people live. Wind power is not cheap. So there's a problem that's the same problem that people have faced for literally centuries. That is market. You have to be able to get your cheap goods to market. And how do you do that? That's the question. Now there's another complementarity with the fact that wind power is kind of something that exists in one part of the U.S., and solar power is something that exists more strongly in our southern states and especially the Southwest. So what we wanted to do in our study was look at, could you take the complementarity, solar power during the day when you need it for peaking power, wind power at night, in different places, could you take those and put them together? So that's a weather question, but there's an overriding weather question on top of it, which is this. The intermittency can't be dismissed easily. You really have to have, if you have a system, you have to be able to support power every minute, every hour, all the time. You can't just sort of say, well, we'll just turn off the power for a few days if it gets too cold and dark like it did here in Colorado, where we had like 10 days without sun or anything last November, and a lot of people with solar systems were saying, gosh, I didn't really appreciate this part of it. So the problem there is really a problem of weather scale. And my apologies for showing this nerdy meteorologist diagram, but what you're looking at on the left side are powers of 10 in the amount of kinetic energy available per linear meter. So what's interesting here is that the amount of energy as you go up this scale goes up by orders of magnitude. And this is what's called a spectral analysis. And it shows that the energy scales of the atmosphere are huge. They're very large. So this little green line is the size of the United States 48 states. So this is logarithmic in area on the bottom. And right now, this red line is the area where we're sharing electricity using our AC transmission and distribution systems. So you can see right away a giant problem. That is, we're basically have limited energy available over a small scale that we're currently using, and yet if you get up to the full 48 state scales, there's 1,000 times more energy density. So what does that really mean? Let's make it simple. You want to build a domain big enough where you share the energy so that wind isn't blowing in one place, it's blowing in another place. So that's the key to our study, and I'm going to go through it fairly quickly. Here's an example. There's a giant high in the eastern United States. I just picked this up when I was doing a talk. There's a giant low in the west. That means the energy that you want to get, you have to be big enough so you encompass the windy and non-windy areas. So we collected what amounts to 40 billion pieces of very accurate weather data. We basically built the diagnostic high time resolution weather model, the RUC model, now the high resolution rapid refresh. We ran this for 3 years. We quality controlled it. This is hub height wind. So you're looking at the areas that are windy are red. The areas that are not windy are blue. And you can see these big storms sweep across the United States. But our problem is we have to design a system that puts up wind turbines and solar plants so that we get power every hour. That's the key. Here is the same thing except it's solar, and this is in near the winter solstice in December, and you can see the amount of solar power. Most of the time it's gone. I'm surprised that poor David Grimes up in Canada gets any solar power at all in the winter. But in any case, you can see southern United States still gets a fair amount. So that's what the data looks like. Again, 40 billion accurate, careful of the amount of PV power available and the amount of wind energy available. And you can't just do that. You also have to jump in and take the electric load. So this is the whole United States electric load as a function of time. These little notches that you see are actually the weekends. And you see a couple things here. You see the entire United States has a summer maximum of air conditioning, where it gets up close to 800 gigawatts of electricity being used. So we wanted to have a system, to design a system that used large-scale wind and solar energy and delivered to 130 markets. So you see here what the each week looks like. This first week in December, you can see those little bumps. One of them is the morning rush hour, one of them is the evening rush hour. So that's the total load which we had over the United States. And a final thing which is absolutely crucial, you have to be able to make a national market. Now, people have figured this out before. There's a very nice passage in Stephen Ambrose's book where Abraham Lincoln says, we have to have transcontinental railroads. We've got to put this together. There is President Eisenhower. I might point out these are two Republican presidents. I don't know why I think of that. We had President Eisenhower who said an interstate highway is crucial to make our goods and services for this country. So my argument here is high voltage DC with its two advantages. One of them is long distance transport with minimal losses, and the other was high capacity. And these are not, you know, pie in the sky technology. We have HVDC lines. We have them being built in Europe. They're built in China. We used actual costs for everything. So this is a hypothetical network, and we're going to have this system that designs where you would put wind, where you would put solar, with the following ideas in mind. One of them is you want to minimize total costs. That's that bucket of money. So you want to minimize total cost, but you have to pay all the costs associated, mortgage and capital costs of the solar plants, the wind plants. This study that I'm going to show you is one of hundreds that we've done, but I'm going to show you a natural gas one. So you have to pay for the natural gas plant and so on. But it's subject to the actual sun shining and wind blowing over the whole United States. And when you don't have enough, you can always make it up with a dispatchable so that you meet for every hour for 3 years, 27,000 hours, you meet the total US load for 130 load areas. So this is a giant computer program that we did to design this. It's described in a peer-reviewed paper. If you want to get into the math, again, it's pretty amazing to me. You can put this data, the weather data, the load data, into a computer, let it crank for a week, and it literally does crank for a week, and it tells you a system that would deliver low-cost power. So how do we start? We start with the existing power system today. So today's existing power system, we have hydroelectric, gas, nuclear, coal, everything. And again, the test that I'm going to describe, we used basically everything but coal, and we do have coal tests also, so I'm going to show you those too. So here's the result. You put it in, a computer cranks away for a week, and what you see are a couple things. These green areas are where it put wind turbines. Ends up with about 200,000 wind turbines, 3 megawatt wind turbines, 200,000 of them. These black lines are the power lines that it built. So the thickest black lines are 12 gigawatt high voltage DC, and the system picks some areas where it doesn't really use the power lines much. So when we run the simulation without those, a lot of these drop out. So it builds a network over the United States that can distribute the wind and solar power. The red things are the solar areas, the blue ones are hydroelectric dams, the black ones are coal. So it builds a system over the United States that's dominated by wind power, but it basically always has natural gas power as a backup. So a design system using Energy Information Agency estimates of what the costs are going to be in 2030 that delivers power. Now, let's find out what it costs and how much carbon. That's the key question. Because I just made a qualitative argument gee, if you can distribute the power over the whole US, it ought to be cheap and it ought to be reliable. So here's what it looks like as it's running. You're actually seeing by the color of the blue how much wind power is available in the network. The dark lines are when it's pumping power. When the sun comes up, you see the red areas as the solar power becomes available. If you watch this for a while, you can see what's happening. It's taking power from the wind triangle and pumping it to the coasts. It's getting peaking power from its solar plants to minimize the amount of other power that it needs. So a computer, a linear programming to create a national system. What does it give us? Well, let's start with 2012. In 2012, we had 2.1 gigatons of carbon dioxide, and we were paying 9.84 cents in the United States. The Energy Information Agency estimates that in 2030, we will have gone down 9%. 9% by 2030. If that's what happens, there's really no hope. Price, they estimate, is $11.50. Now I'm going to show two simulations that we did with our simulator for 2030. First one is the one with coal. So if we just build our high voltage DC network, national market, and let coal compete, your price comes down, but your CO2 emissions go up by 24%. So that's simply a statement that if we built a high voltage DC network today, we would actually save $25 to $50 billion. It's a good thing to do no matter what. Build a national market. It's always a smart thing to do. Now what happens if we allow our wind and solar to join in? The answer is, in the United States with an HVDC network, we do have prices. This is our low-cost renewable, high-cost gas scenario. There's what it shows is 10.7 cents per kilowatt hour, less than we probably are going to end up paying if we don't do anything, and 86% reduction in carbon dioxide. So there is an answer. And that answer is you can reduce CO2 without increases in costs, a politically palatable thing. I'm not going to talk about it, but we have a similar study for all of Europe where we put an HVDC over Europe. We did a similar study for China, same thing, Europe, same thing, United States. If you have a large market area, wind and solar competes because it can find the cheap areas for wind and sun and pipe them to where the markets are. This is my son in front of his Tesla. I don't know why he's driving a Tesla and I'm a poor scientist driving a beat-up fossil fuel car, except that he's a cardiologist and I'm a scientist. I guess that's it. But I want to make a point, and that is, if you get the electric sector done, then you can electrify transportation and all those wonderful things that Amory Lovins talked about. So the solution to the biggest problem of the 21st century, 3 mature industries and 1 coming on strong. One of them, of course, is wind turbines. Another one is solar PV, large scale. Third one is high voltage DC. These are pictures from Sweden that I took, the 2 on the left. And then finally, batteries are coming on strong. This is Elon Musk's gigafactory. So my final comment is the time for sort of semi-solutions, or if we all do a little, has probably gone by. There is an answer in what we're talking about in this meeting. We do have the technologies in hand. High voltage DC, wind turbines. We used the best estimates of what those are and said the major industrialized economies of the world can do this without huge economic harm if you just do the weather right. So thank you.
That's an excellent talk. And I want to take a few questions, 5 minutes for questions, even if they're a bit beyond. We'll catch up later. Is there any question for Dr. McDonald? Please go. So we have two questions, one from Dave and one from Rashad.
Sandy, this is Dave Jones with Storm Center Communications. I was just wondering if the work that you're doing is in conjunction at all with like Department of Energy or Oak Ridge, or because they're looking at the exact same sort of things. They don't have the weather expertise, but I'm sure that's what NOAA can bring to the table. Is that something that that you're working on together with DOE?
Yes, I think it's fair to say we got huge help. Particularly, we got huge help because National Renewable Energy Lab is nearby. When we started on this project, I think we were sort of like school children. We just learned everything we could. We can also make different assumptions. I think policy-wise, there's this target of 2050. We can make an assumption 2050 is too late. Let's work on 2030. So like some of the energy futures and other studies, they were constrained by requirements that there has to be stuff in every state and those kinds of things. We just basically let this computer program say, can we build a low-cost network with today's technology? So they were, I've had a chance to brief this top levels Department of Energy. They've been very helpful and supportive. Likewise at the White House, I briefed the President's Energy Advisor. So we've gotten lots of support, and I think that being within NOAA and the government, that's been very helpful.
I think very exciting talk, and I was very thrilled to see all those simulations. The questions that I have is regarding their validation. So to convert these simulations to a level where policy can be adopted based on that, what is your validation strategy?
What did we do to validate it? One thing we did is we actually, and I don't show it, this is a short talk, but one thing we did was we ran it against today's technology. In other words, we took today's prices of wind, solar, coal, everything, and we ran the simulation, and it came within actually a few percent of the amount of wind that's out there, the amount of solar that's out there, the amount of coal. In other words, the simulator basically was able to get very close to what we have today. We have tested it in a lot of other ways. I shudder to say that our supplemental that went with our science paper is 65 pages long with a lot of detail, but it has been validated in a lot of ways.
I would like to point out that we carry out a similar study in Spain, more modest, obviously. We get also similar results. So you don't need a big country to obtain this balancing issue. Even in relatively small country as Spain, you can get even baseload power from wind.
Yeah, I want to just make a comment on that. So what you have with the U.S. and China and Europe are sort of big political domains within the mid-latitude windy belt. So that's one thing. When you get into the Mediterranean or India or others, you have an alternative approach which is more dependent on solar power and those things. The usual sort of simple statement right now is if you take Energy Information Agency estimates of solar power plus storage, plus large-scale storage, you double your cost of energy. So I would be interested in knowing if you sort of solve that problem or whether you have enough hydro or so on. But I actually want to make the larger point that there is no political domain over the earth where we can't look at the possible renewable resources and the existing things. Canada has a lot of hydropower. India has a lot of solar power. You can't look at them and then minimize their costs to get to very low carbon. And I think that's what we got to do. So thank you again.
Fantastic. Thank you very much.